Welcome, dear students. Welcome to nuclear physics lecture. I'm Dr. Parvez Ahmed, and this lecture we will talk about the mass defect. So let's start our lecture with the mass defect. What is mass defect? So as you know that mass defect is basically the difference between the mass of an atom and the mass of its individual particle. So just like you can see it here in this particular figure, here we have the mass, that is the mass of an alpha particles, which is equal to 4.00260 AMU, which is smaller than the mass of the individual particles, that is protons and neutrons, two neutrons and two protons. If we sum their masses, the mass of the individual particles, so it will be greater than the mass of the helium nucleus, sorry, helium's atoms, that is with two protons, two neutrons and two electrons, because here we have two electrons, which means that we have a helium nucleus. So what is mass defect and how we can calculate the mass defect? So just like we mentioned in the definitions, mass defect is equal to calculated mass of the constituents minus the Mayer mass of the nucleus. So what actually we do, we basically trying to find out the difference in the mass. So the difference mass is equal to total mass of the protons and the neutrons minus the Mayer mass of the nucleus. That is, first of all, we add up the total mass of the total number of the protons and the neutrons, and then from that particular mass we subtract the mass of that particular nucleus. So how can we do that? I mean, mathematically we can write, this same statement just like this, that is mass difference is equal to uh, the atomic mass, uh, and that is the number of the protons, sorry, the atomic number, that is the number of the protons or the number of the electrons, plus the number of the neutrons minus the mass of the atom, that is the total mass of the atoms. Or we can write, in sample words we can write it, that is the mass difference is that is the mass of the protons plus the mass of the neutrons minus the mass of the nucleus. Why are we writing so? Because here we can neglect the mass of the electron, because the mass of the electron is very very small as compared to the mass of the protons or the mass of the neutrons. So binding energy, that we denoted by E with the subscript B, is equal to mass defect multiplied by C square. So binding energy, EB, which equal to delta M. Delta M, that is mass defect, should be in units of AMU, multiplied by the value of the C square, which in term of energy units equal to 931.5 mega electron volt. Uh, the ratio of the mass defect, that we denoted by delta M, to the mass number, that we denoted by A, is called the packing fractions, that we denoted by F. This is another quantity of packing fractions. So what is mean by the packing fractions? So packing fractions is the ratio of the mass defect, that is delta M, to the mass number, that is A, and this is given by the fractions, the packing fractions we denoted by small f, and it is given by f is equal to delta M divided by A. So the units for delta m, you know that delta m we measured in atomic mass units, and A is basically the number of the nucleons. That is, we have atomic mass. So atomic mass is basically a total number of the nucleons in a particular nucleus. So we can write it. I mean the packing fractions that we denote by F can be written as delta M divided by A, which is equal to uh, the mass defect. I mean, you know that just like we discussed on a previous slide, the mass defect is given by these equations divided by uh, the mass number, that is capital A. Similarly, just like the packing fractions, we have another quantity, another number that we call binding fractions. I mean, just like packing fractions, we have a binding fraction. So what is a binding fractions? A binding fraction is basically the ratio of the binding energy to the mass number A. Let me repeat it again. What is a binding fractions? Binding fraction is basically the ratio of binding energy to the mass number A. It is denoted by uh, FB, FB, and is equal to the binding energy that we denoted by EB divided by A, that is the mass number. So here the binding energy we denoted by the binding energy we have the units, that is mega electron volts, and A again is the number of nucleon in a particular nucleus. So the binding fractions mathematics is given by EB, and E for the binding energy and for the atomic mass, and equal to are given by this particular equation. That these equations, this is for the binding energy, and A is for the mass number. I mean, this is how we can calculate the binding fractions. So binding fractions of different nuclei represents the relative strength of their binding. I mean, maybe some people may ask the questions that, well, what for we need the binding fractions, or what for we need to calculate the binding fractions. What is the importance of the binding fraction? May be more precise to be asked by some of the people working in this particular field. So for the information of those people, it's been important to mention it here that binding fractions of different nuclei represents the relative strengths of their binding. Just like, for example, you can see it here. We have, or we can take the example of the alpha particles, and alpha particles, you know that it's combination of the two protons and two neutrons, and collectively the mass of the alpha particle is equal to 4.00153 unit. But individually, if you look at the mass of the two protons and two neutrons, so simply what actually we need to do, we multiply 2 with the atomic mass of the protons, and with the atomic mass of the neutron. So we get the mass of the particles. So total mass of the particle is equal to 4.03188 U. So from here you can easily find out the mass difference of the alpha particles and the individual nucleons that constitute the alpha particle. We remember 1 U is equal to 1.66054 into 10 raised to power minus 27 kg, which in term of energy units is equal to 931.494 mega electron volt for C square. So the mass defect is equal to 0.030 U. So binding energy, it means that if we convert this value into binding energy, so it's equal to binding energy of 28.3 mega electron volt. So what it means, From here we can calculate the average binding energy per nucleons, that is Fb is equal to that is we have to divide 28.3 by the total number of nucleons, that is 4. So we get the average binding energy for nucleons and is equal to 7.04 mega electron volt. So comparisons, a binding energy of an electrons and a hydrogen atoms with the binding energy of the alpha particle, just like you can see it here in this particular example. I mean, here we have the binding energy of an electrons in a hydrogen atom. This is an example. I mean, this sketch basically represents the hydrogen atom, and you know that in hydrogen atoms we have an electron revolving around the nucleus and a protons that reside inside the nucleus. So the binding energy of an electron hydrogen atom has an energy that's equal to 13.6 electron volt. So if you want to compare that with the binding energy of the alpha particles, that is I mean with which the nucleon inside the alpha particles they are being bonded, so it's equal to almost equal to 28 mega electron volt. That is what it means. It means that the nuclear binding energies are on the order of millions times greater than the electron binding energy of the atoms. An example, you have seen it by yourself. I mean, you have seen that it's the binding energy for the electrons. I mean, you want to separate the electron from this atom, hydrogen atom. So you only need to supply this much of energy, that is 13.6 electron volt. But if you want to break the bonds between the nucleons inside the alpha particles, so what actually you need to supply, you need to supply this much of energy, that is 28 mega electron volts of energy is needed to break these bonds or to break this nucleus. So this is a short comparison of the binding energy of an electron in a hydrogen atom with the binding energy of an alpha particle. So that's all we have for this lecture. See you uh, for more lecture. Till then, bye bye.